Hey everyone, welcome back to our final lecture of CS196 this semester. Today we're talking about two-pointers, a really important technique in coding interviews that you'll definitely see down the road. As always, I have Discord open up here, so if you want to ask any questions, send me a message, I'll be able to see it right there. And this is the final lecture. This is my last lecture forever, the CS196 lecture. It's been a really, really fun ride, and I'm really glad that it's an opportunity to teach you guys concepts that I'm passionate about and I think are really useful. Sammy feels the exact same way too. So, quick announcement before we start. Today is the final CS196 lecture. I've said this so many times already, I still really can't get over it. And a reminder, to complete the extra credit feedback form, it's worth 3% extra credit, just free points here. And if at least 80% of the class fills up the form, you'll also get an additional 1% extra credit. So collectively, you guys can get 4% extra credit if you just fill up this form. So please fill that up. It's going to help us out a lot, help the new instructors out a lot. Also, your final project videos are due on midnight reading day. I was confused about this. You guys have reading day to work on it, but please try to get it in as early as possible so you can just focus on finals. You guys have done great work so far. The midterm presentations were amazing. So I'm sure your projects will be looking great too. So please get it on ASAP and please fill up the extra credit feedback form. So let's go over our objectives today. So firstly, we want to go over what is two-pointers and give it like a high-level overview. Then we're going to go over a few popular reverse two-pointer problems, two-sum and reverse string. Talk about maximum subarray size k, which is a same direction two-pointer problem. Talk about this, how we use two-pointers in the sliding window, link it back to Sammy's lecture, and finally, other two-pointer problems and general coding interview advice. I don't think this lecture is going to be super long because two-pointers is pretty straightforward. So let's give this a pretty high-level overview. Two-pointers is pretty self-explanatory. Instead of using one pointer to iterate over a list like data structure, we use two. So if you think about a for loop, for example, you'll do something like for I in range x, or for I in range len of array print array I, right? That's a single pointer. We're treating that counter as a pointer. What we're going to do now is use two pointers to optimize and solve more complex problems. This is something that you will not see probably in 225 and 374, but it's something that optimizes code a lot and often what interviewers are looking for in coding interviews. I myself, this season alone, have done at least 2 to 3 problems that have utilized two pointers. So it's a really useful, really popular question that we aren't taught explicitly, but I think you guys will really enjoy learning. So some problems require us to have pointers moving the same direction, others require us to move in different directions. And this is important because it helps you understand the kind of problem you're looking at and basically use these patterns to solve the same problem over and over again instead of trying to solve a new problem every single time. Finally, this method allows us to save space and time because we're instead of using recursion or a heavy data structure, we're using two pointers, and it's usually O of n or O of n squared, something like that. Pretty quick. So I think the easiest way to explain this is with an actual problem. So let's go over to sum 2. So the problem is given a sorted array, so sorted from descending to smallest to largest, we'll call this array numbers, return the index of values that sum up to a target called target. There's not guaranteed to be a solution, and your answer should be one indexed. Key point there. So let's say we're given this input here. We want to find two numbers that give the largest sum. The sum up to our target 9. So we look through here, we see that 2 and 7 add up to 9. So we return 1 and 2, because remember our array is 1 index, not 0 index. There's a bit of complexity just to make the problem a little harder. See how well you pay attention to things. So we get index 1, index 2, and return that. And you can try this problem out in LeetCode. I actually strongly advise you do that. So let's take a look at this problem and how we're going to solve it traditionally with a double for loop. So intuitively, you're probably going to think, all right, I think I can find out every possible permutation using a double for loop. And someone just asked here, index 0 and index 1. Nope, you would be correct if that was a regularly indexed array, but this is a one indexed array. So unfortunately, it is 1 and 2. That also caught me up when I saw this problem the first time. So in a double for loop, what we can do is essentially find out every permutation. And we can basically see, we have all these sums here, what's the final answer? So this is a different array, it's slightly larger, and our target is 10. So we start off with our value here. So you go, this is our first pointer, so for I in range, this value, for j in range, this value, we get the sum. So we can keep moving this pointer. We can keep moving this pointer down, get the sum of that, get the sum of that, get the sum of that, get -5 plus 7, -5 plus 9, -5 plus 10. Nothing of those adds up to 10 yet. So we go all the way back, increment our outer loop, bring our inner loop forward one, and then calculate all the sum again. So -3 plus 2, -3 plus 3, -3 plus 5, etc., etc., etc. Obviously, this isn't that smart, but it will definitely get us the answer, because eventually we'll reach a permutation where we have 3 over here and 7 here. So intuitively what we're doing just here is we're having a double for loop where we have our outer loop, so it's for I in range, whatever the len is, and our inner loop is going from whatever I is to the end of the array. And we're just calculating the sum of every possible combination here. But notice this is really expensive. This is going to be O of n squared, and although it's O of 1 space, it's slow. And we're not utilizing the fact that our array is sorted. So how can we utilize this fact and use 2 pointers for our benefit here? So let's go down to our 2-pointer example here. So we know our array is sorted, and we also know what the start value and the end value is. So what we can do is keep a running sum of what we have. So what that means is, I'm going to take the value of pointer 1, that's -5, the value of pointer 2, which is 10, and I'm going to keep, I should have this out ready, a current sum. And our current sum at the moment is 5. So I'm going to keep that here. So 5 is less than our target. So we know that we want to get a number larger than 5. So since our current sum is less than target, we want to get a larger number. So how do we do that? Well, we can do that by moving our pointer over here up by 1. How do we know this is a larger number? Well, this is a sorted array. So that means as we move along this way, the numbers that this blue pointer is going to get are larger. Similarly, if our current sum was larger than the target, then we want to make this smaller. So we make this smaller by simply pulling this back. So let's see what we have now. 10 and -3 is 7. Still too small. Let's go up one more. 10 and 2 is 12. Okay. Now 12 is a little different. It's larger than 10. So since our number is larger, we want to make this current sum smaller. We can make it smaller by moving this pointer down 1, which gives us 11. Still too big. Bring it down one more time. Gives us 9. This is smaller than our target, so we bring this up 1. Now we have 10. So this is pretty straightforward stuff. We're essentially just using 2 pointers to get a sum of that we're working with here. The benefit of using 2 pointers here is that since our array is sorted, we know exactly how to move our pointers to get its maximum sum. So the benefit of this is, sorry, just jump back here, is that our double for loop is O of n squared. But this case here, we're going to keep going up until our pointers cross over. Once they cross over, we know for a fact that there's no possible combination that works because we've tried every single element, right? So let's take a look at this in code, because I think that'll be a little clearer. So first we're going to get a pointer to the first element and a pointer to the last element. And we're going to iterate while P1 is less than P2. So while the blue pointer is less than the second pointer, we keep doing this iteration. The reason for that is once they cross over, we know that there's no combination. We're just going to repeat those steps again and basically have like it's an impossible sum here. So while we're in this for loop, we calculate the sum. The sum is simply whatever P1 is at and whatever P2 is at. Get the value that the index is pointing to and keep that current sum. If we reach our target, then we know we just have to return P1 plus 1 and P2 plus 1. The reason we have the plus 1 again is because we're not 0 indexed, we're 1 indexed. And that will just throw you off. There's no need for that in the question itself. It really doesn't add anything, but it sees who's paying attention to the problem, being more detail oriented. But let's say our current sum is less than the target. If our current sum is less than the target, that means we want to make our current sum larger. To make our current sum larger, we simply have to increment this pointer. And we know this is always going to be larger because our array is sorted. Similarly, in the other case where our current sum is less than target, greater than target, my bad, we want to make the whole current sum smaller. So to do that, we just move P2 by -1. And you can see here, when we have this array here and a sum of 10, we get an answer of 4 and 6. So let's double check that. 1, 2, 3, 4. 4 is 3, 5, 6, 7. That's 10. Let's do a quick analysis of this algorithm. Because it seems very obvious, and you're like, okay, it's either a double for loop or it's this two-pointer thing. Two-pointers are kind of weird. I don't really like it that much. But let's take a look at how much faster this is. If we look at the complexity, time complexity is O of n instead of O of n squared. That's a whole order of magnitude smaller, which means if you have a very large list of like 1 million elements, you will be so much faster than someone doing a double for loop method. And the reason it's O of n is because there's n elements and each is visited at most once. So people who are like watching the code will understand that we're only going to be going through this n over 2 times. We're only going to go through this for loop n over 2 times because the moment we see a crossover, right? The moment these 2 pointers cross over, we stop the code. However, the way complexity works is that if something is n over 2 or 5n or 100n, that's still O of n. That's just how complexity works. You learn more about that in CS173. Space complexity is O of 1. It's constant space because we only create 2 pointers. Apart from the 2 pointers that we create and the values that we're returning, we're not actually doing anything else. So space is O of 1. Any questions about this initial 2-pointer algorithm or problem? I think that makes sense. Let's move on to the next one then. Something a little more complicated. So a little more involved. Reverse string. So the problem is, given an array of characters S, reverse the array in place with O of 1 space. So that means we can create no extra data structures, and we have to edit the original array. So this is a little trickier because because of the extra constraints on the code, on the problem, sorry. So again, it's your own leak code. You can try it yourself. So let's actually look at this again with TwoSum. Okay, I think that's a very easy way of going about it. So if we have this array, hello 196, how can we reverse this in place without creating any extra data structures? Well, a really easy way of doing this is simply bringing these 2 outside pointers towards the middle, so incrementing pointer 1, decrementing pointer 2, and at each iteration, we simply swap those 2 values. So I'll show you what I mean. So pointer 1 is pointing at the 0th index, pointer 2 is at the last index. What we're going to do is swap them. Oops, sorry. 6 and H, like so. Now we go to our next iteration and we increment, decrement, and we swap again. So 9. I know there should be those little speech marks, but this is to save time. Again, we decrement. 1L, decrement 1 last time, so this is going to be space, and this is going to be, another L, and now we're at the same value. So the condition for our while loop here would be while P1 is once again less than P2. And as you can see, our final result is hello 196. The reason this works is because the reason this fits the constraint, is all we're doing is swapping these values. We're swapping the values in place, and we're not creating any extra data structures. So let's look at this code now and see if we can find a pattern with the previous one. Okay, so first things first, I do want to talk about how another way we could solve this. Instead of doing all this code, you could just do s.reverse. That's super fast. It's actually very fast in Python. You could also do something like do a slice like this. And this is actually really, really fast in Python just because slicing is super optimized in Python. But let's say your interviewer wants to be really strict and says, I want you to write actual code. So similar like the last one, we get the pointers, P1 and P2, like so. And we iterate while our pointers don't overlap. So while P1 is less than P2, we simply swap SP1 will be whatever is at pointer 2, S pointer 2 will be whatever is at S pointer 1. And then we increment and decrement the left and right pointers respectively. So now, when we try this again, you can see that we get the exact same answer that we saw before. And the exact same answer before was hello 196 reversed. So again, this problem seems pretty easy once you know the answer, but if you're in an interview, it's very easy to come up with very complex answers that aren't effective. But if you know this trick here, you'll save a lot of time and impress your interviewer. So now let's go into analysis of this again. Because in an interview, you should be talking out loud, you should be explaining why you're making the decisions you're making, and understand the complexity of your code. So 2-pointer analysis here, our time complexity is O of n, because again, we're only doing O of n over 2 iterations, max, but we need to swap, because we're swapping n over 2 elements, but that's still O of n, because O of n over 2, O of 5n, O of 100n, again, all equates down to O of n. Because n over 2 is just n times a half, the half is a constant. So constants we could remove from time complexity calculations. Again, you'll learn more about this in CS173. And the space complexity, once again, is O of 1, because the only space we need is the 2 pointers. So you see here, we're able to optimize problems by using 2 pointers because we can reduce our space a lot, and we can often reduce our time complexity by at least like an order of magnitude. And if we look at the code themselves, they have very, very similar patterns. We simply define our 2 pointers, we do a while loop while they don't intersect, and then we do our computation inside. Pretty straightforward. What you'll notice, however, is that in these kinds of problems, our pointers move in opposite directions. So they're going from our left side to right side, and they're coming in towards the middle. So let's actually take a look at a problem where our pointer's moving in the same direction and how we're going to use that. So let's look at this problem. It's called maximum subarray of size k. So given an array called number, return a subarray of size k with the maximum sum. Okay, let's just back up for a second. Didn't we do this exact problem with Sammy? Isn't this literally just a sliding window problem? And yes, that's exactly what it is. Sliding window and 2-pointer basically go hand in hand because keeping track of an actual window essentially means keeping track of the start pointer and the end pointer. And these 2 pointers move in the same direction. So this is where a 2-pointer and a sliding window kind of come together for problems like this. So let's do a quick sliding window recap. We have this array here, we have k equals 2, and we want to get the maximum sum. So which contiguous subarray size 2 has the maximum sum. So this is our little window. We're going to grab our window here. 2 plus 3 is 5, that's our current max. 5 is less than 7, so 7 is our current max. 7 is bigger than 2 plus 4, which is 6. And finally, 9 here is our largest, so we're going to keep 9. Let's incorporate 2 pointers into this algorithm. How could we use 2 pointers instead of sum? Because remember, as Sammy mentioned in his lecture, if we're just keeping track of a window like this, calculating the sum overall is really expensive, and calculating the sum is really expensive when we have to calculate the sum for the window each time. Sorry, someone is saying, is my sound out of sync? Sorry guys, I don't know why that's going on. Hopefully if you just refresh your Wi-Fi or something, or refresh the page, it'll go back to normal. So, as Sammy said in his lecture, calculating the sum every single time is really expensive. It's essentially O of n times k, because you have to do it n times for all the k subarrays. Or sorry, the summation is k, and you're doing it for n subarrays. How do we do this with 2-pointer to make this really fast? So what we can do is calculate our initial sum like so. So we have 2 plus 3, which is 5. So we're going to keep track of our max sum. Max sum. And we're also going to keep track of our current sum. Like so. So our max sum at the moment is 5. That's also our current sum. So let's slide our window across. And in this case, that simply means moving our 2 pointers up 1. Now what you'll notice here is that even though we're sliding this window, all that's actually happening is that we're removing the bottom element and adding a top element. And that's better demonstrated here. Let's say we have a window of size 3. If we want to slide this up 1, notice we're just removing the lower 2 and adding this upper 2. We slide up 1, we're removing the bottom 3 and adding this upper 7. So we don't have to calculate this entire sum. Let's just remove this value and add this value to our current sum. So 5 minus 2 plus 4 minus 2 is 3 plus 4 is 7. Somebody calculate me if my arithmetic goes wrong. We check which is larger, max sum or current sum. Max sum is larger, so we keep it as our new max. So current sum is larger than max sum, so we swap them out. Again, we go over one more time. The sum is 6. We go over one more time. We get the sum again, which is 9, and then our max sum is 9. So let's look at this in code, because I implemented it slightly differently to Sammy, but they'll both be about the same in space complexity and runtime complexity. So what we want to do is first initialize those pointers. So we have P1, which is going to be 0, our left pointer, and then P2 is going to be the length of our subarray. So that's simply whatever P1 was plus K minus 1. We do the minus 1 simply because we're 0 indexed when you're writing code. We want to get our current sum, which is going to be the summation of P1 to P2. And then we have current sum, which is going to be the same as max sum at the moment. So while P2 is less than the end of the array, we're going to keep track of our current sum by removing the bottom value and incrementing the new value that we're going to add. So as we saw before, if we're sliding from here, we subtract 4 and add 7, which is exactly what we did in that step. And then we increment our pointers and we get our new max sum. Very, very easy. The difference between mine and Sammy's code is that Sammy doesn't initialize his max sum array. He does an if statement instead within the loop. Both will work. I like this way more just because because if statements take time in code, anything in code takes time, but if statements take time because you have to have 2 different branches open. So I like to do some beforehand, but both of them will essentially be the exact same speed, exact same runtime. And now if we run this code, we get an answer 9, which is what we expected. If we increase our window size, we'll see that our answer corresponds and matches with that. So 13, which makes sense because 4 plus 2 plus 7 is 13, etc., etc. We can make minor optimizations with this, but this is essentially the answer that your interviewer is looking for. So let's go over complexity again. Sammy already did this, but with a question like this, if we're calculating the sum each time, it's O of n times k. But if we're doing this method, it's simply O of n, and the space is also going to be, or the space will be O of 1, again, using 2 pointers method. So these are 3 examples. What I want to highlight is that this is a very strong pattern with 2-pointer questions. You initialize your 2 arrays, you get some prior calculations, and you iterate. For questions where they're in opposite directions, you iterate while P1 is less than P2. If they're moving together, you simply go to the end of the list. And you do whatever computation you need to do underneath that. So that's what I wanted to touch on regarding 2 pointers. Do you guys have any questions about that? And yeah, the animations are kind of janky. I just thought this would be a easier way than making like 100 slides. So when you're reviewing it later, you won't have to go through all of those again. Okay, if there's no questions, then we're going to go to a super quick Kahoot, mostly just for attendance, honestly. I like the new Christmas theme Kahoot they got going on. A little design there, a little fun music. let's start the Kahoot. It's going to be pretty easy. It's 5 questions. The first one isn't even a real question. So after watching lectures, how confident do you feel in these concepts? Good to see. I'm glad a lot of people are understanding it. For the people who are really confused about it, please post on Piazza, make a question. I see somebody accidentally clicked it. I'll lower the music if it's too loud. But I see someone accidentally clicked it. But if you are struggling with it, please let us know. We're more than happy to help, even though it's near the end of the semester. I'm really sad that Rohan Suresh isn't up here. Disappointing. True or false? Creating pointers for 2 pointers is O of n space. I'd read that title a couple times before answering if you're unsure. If you're having latency issues, just answer any question that you can. You'll get credit for being here. Sorry about your internet dying. I think a couple people are having issues with my stream right now. Let's jump right ahead. Alright, creating pointers for 2 pointers is O of n space. Okay, this is a bit of a mix here, but this is false. The reason for that is because we are creating 2 pointers, 2 being a constant number. And as we saw previously, all the problems we saw were O of n space for the most part. I think all of them were O of n space. O of 1 space. Okay, let me backtrack because I misspoke. Creating pointers for 2 pointers is always going to be O of 1 space. Because we're only creating 2 pointers at a time, and we know that it's a constant number each time. We're not doing a for loop to create these pointers, so it's O of 1 space. And as we saw in those previous problems, those are also all O of 1 space simply because we only had to keep track of the pointers and maybe a few extra variables here and there. We weren't like making a dynamic list that was growing or like a hash map or a set. So it's O of 1, and creating pointers specifically is always going to be O of 1 because we know exactly how many we're going to be making. So good job, guys. True or false, 2 pointers won't work on a doubly linked list. So think about how doubly linked lists work. You have a linked list that you can go in both directions of. What is that essentially? Okay, so false was correct. So let me explain why. So if you're not familiar with a doubly linked list, it's my apologies. Essentially, a linked list is sort of like, it's a list. You have a bunch of nodes and they're joined together by a single arrow. So number 1 points to number 2 points to number 3 points to 4. In a singly linked list, it's in that order. So 2 points to 3. So 2 cannot go back to 1. Under no circumstance, unless you know what the previous value is. But in a doubly linked list, 1 points to 2, but 2 points to 1 and 3, 3 points to 2 and 4, so you can go forwards and backwards in that list. So essentially, it'll work exactly like how one of our arrays work. So we can still have 2 pointers, one pointing at the head of the linked list, one pointing at the tail, and we can go in like a 2-pointer sort of manner. So good job, guys. Next question. Time complexity of 2 sum. So we're going over this array and we're doing n over 2 calculations, or n over 2 iterations, sorry. So what is the sum? Alright, great job. Almost all you got it correct. It's O of n. The reason it's O of n is because we're going through this array and we're doing n over 2 loops, and n over 2 loops is going to be O of n because we removed the constant value from there. Good job. Final question, the space complexity of 2-sum. If you want a hint, think about a previous question we had about space complexity. I think that's just done by 2-sum 2 because it's completely coding over their questions. Alright, awesome. Again, most of you got it correct. It's O of 1 space. The reason it's O of 1 is because, especially in 2-sum, we're only keeping track of a handful of variables that we know beforehand. It's a constant number of variables that doesn't change regardless of how big our linked list is or our array is. So it's going to be O of 1 space. Great job. Let's quickly go through the podium. There's top 3. Great job, you guys. Let me close out of this now. Okay. So I hope that stuff made sense. 2-pointers is a relatively straightforward concept. The only way you can really get better at it is by practicing it and seeing what kind of problems you can apply it to. There's definitely a pattern and there's definitely a specific type of problem that it's useful for, but it's very versatile, and I think the best way to learn it is to just practice using it. So here's some other 2-pointer problems. As you can see, there's a lot of problems. Some of these are very frequent. A lot of companies use these problems, and there's a wide variety of ways you can use 2-pointers. So please get to practicing. If you have coding interviews coming up, I think this is a great problem to get started off with, or a great type of problem to get started off with, just because it's a little trick that does boost you a lot in that interview. So before I leave, I want to give you guys some general coding interview advice, because I think it's really, really easy to just get stuck when practicing questions. That isn't the only thing. In your interview, make sure you ask lots of questions. Asking lots of questions indicates to your interviewer that you are a proper software engineer. You ask questions about the problem and you want to know how to do it properly. It also gives you time to sort of have that problem kind of ruminate in the back of your head while you're talking and asking questions, so that once you're done talking, you can just start writing code. Talk out loud a lot. This is a skill that is definitely acquired. It's not easy to do, but while you're writing code, talk out loud a lot. Say, so I would use this because of this, and I want to do this because of that, blah, blah, blah. Talk out loud a lot so that you can explain very clearly to your interviewer what you're doing and save time. And discuss the pros and cons of design choices, even if they seem obvious to you. So for example, for that first question that we did, we could have just said, even though we're not going to use it, we could say, oh, intuitively, I might want to use a double for loop, but I would make it even faster by using 2-pointers. And interviewers love that. They love seeing that you're making these design choices actively. Finally, slow down in your interview. Be clear and confident. Don't be rushed and messy. Even if you're running out of time or you think an hour is not enough or 45 minutes isn't enough, be very clear, because if you did a good job in the interview, that's better than, and you were clear and concise and you were explaining your concepts well, that's better than having like this sort of messy solution that might work, but they don't know because you didn't explain it well enough. While you're writing your code, use descriptive variable names. This will save you so much time. If you're using things like X and blah, you're going to be so stuck when you're trying to debug later on. Use descriptive variable names. It'll save you a lot of time. Think about edge cases. Obviously, don't do this while you're writing code, but talk about edge cases after you write your code is a great way to let your interviewer know that you're thinking about these things and you are a proper software developer. Finally, don't nitpick your code too much. I think I have an issue with this a lot, where I will try to fix this one weird line or this one weird syntax thing, and I waste time. Don't do that. Try and get something down. Syntax doesn't matter. Just move on. Finally, I want you guys to try to practice understanding, solving problems, not just memorizing them. I think a lot of people will tell you just do lead code, and fair enough, that's a really good way of getting good interviews, but it's only if you see problems that are very similar to what you've seen. Try to understand how you're solving these problems, understand the concepts. That way, if you see something slightly different, you can modify the concept that you learned. Practice lots of problems. I know I said it's not the best way, but it really is, I think, the only way to get good at these problems. If you can understand how you're solving them, if you're practicing lots of them, you'll be great. You'll be totally set for any interview. Understand time and space complexity. We touched on that today. You'll definitely cover that in CS196. Understand why your code is running in O of n time or O of n square time. How can you make it faster? How can you make it use less space? Because that's probably one of the biggest parts of the interview. It's a lot of what the probing questions that interviewers ask is, how can you make it faster? How could you make it use less space? Most importantly, don't panic. You will be okay. It is so easy to go into an interview feeling nervous, and that'll ruin you more than not knowing the concepts. Try and stay calm through it. Try and stay calm before it. Try and stay calm after it. I think after it, it's so easy to get in your head about how you did. Finish your interview. Forget about it. Don't think about it anymore. Live your life. You will be okay. The worst they can do is reject you. Oh, my computer froze there. So finally, any questions, guys, about anything related to CS196, related to two-pointers, coding interviews, life, anything in general? Someone asked, how many hours and minutes a day to practice? If I'm being totally honest, I do not practice leak code every day. I don't think it's the best use of your time, especially if you're not in recruiting season. I'd say if you're in spring semester and you finish interviewing, work on your own personal project. It's way more fulfilling, and you'll learn a lot more, and you'll have something on your resume that's really cool to talk about, or you learn a new stack that's really useful. I'd say in the summer and come fall, try and do at least 1 or 2 leak code problems a day. At the very least, do like 4 or 5 a week. I was really bad about it personally. I had to really cram towards the end of my recruiting season, but you'll be fine. Leak code isn't super hard to figure out, especially if you're going to school here for CS. You'll be fine. So if that's all the questions, or I'll come back to the question later. If people are leaving, thank you guys for an amazing semester. I've been teaching class since January, and it's been a really, really fun year. Challenging at times, and we had a lot to shift when we moved because of COVID. But I had an amazing time, and I hope you guys do really great in your finals. You guys worked super hard. I think you guys all deserve A's in all your classes. So thank you guys. Have a great rest of your semester and a great winter.